Okay, so the next session we will now start with looking at classifiers like the nearest neighbor classifier. So, we said that we will talk about um, non-parametric models. So, in the non-parametric models, generally you are not finding you are not characterizing it by a set of parameters, but you are using the training data itself. Okay, such type of methods are called uh, non-parametric methods. So, the simplest among that is what is called the instance based learning or the memory based learning. So, when you get a new instance, you check whether that instance exists in your table lookup. So, the table lookup actually will consist of patterns and their class labels. So, you look in that, and if you are able to find that pattern, then you can say this is your the class label of that pattern. But the problem here is that it does not generalize well. So, in other words, it does not generalize at all, because when you get a new pattern, then what do you do? So, when you get a new pattern, you have to have some default value which you are going to use as the class label of that pattern. So, to take care of this, basically we have the closest to that, which is the nearest neighbor classification, which is a very simple algorithm where when you are given a new pattern P, you find the neighbor which is closest to that. So, if you have a data set which is the pattern which is closest to your new pattern P, and the class label of that will become the class label of this new pattern. So, suppose you have a training set like x 1 y 1 x n y n, and x I is the ith pattern and y I is its class label. So, then you find the distance between the pattern P and each of these patterns and see which is the pattern to which it is the closest. So, suppose d x k, some pattern k in this times P is equal to the minimum distance, then you assign P to have the class label y k, which is associated with x k. So, this is your nearest neighbor algorithm. So, obviously, here the distance metric is very important, because you have to find the point which is closest to that. So, what are the distance metrics that you can use, right? So, what is generally used is what is called the Minkowski distance or the LP norm. So, what is this LP norm? So, suppose I have query x q and I find the distance from some pattern x j, right. Now, this x j will be having a number of features, right. So, the dimension, so you have the value I, which tells you, for example, you may have say d features, in which case this I will be going from 1 to d, right. So, you have to find the difference between the two and take it to the power of p, and then add them all up, and then you get to the power of 1 by p. So, now if p is equal to 2, then you are going to get the Manhattan distance. So, what is this Manhattan distance? You are going to get L2 norm So, we call it as L2 norm between say x 1 and x 2. This will be equal to, suppose each of them has a dimension of 3, okay, for 3 features. then you are going to get it as root of x1 x11 minus x21 the whole square plus x12 minus x22 the whole square plus x13 minus x23 the whole square. So, that is the L2 norm. If you take L1 norm, you are going to get it as L1 of x1 comma x2 will be equal to, like this you will have to take x11 minus x21 plus x12 minus x22 plus x13 minus x23. So, that is the L1 norm. So, that is how you find this distance here. Okay, suppose you have Boolean attributes, it means you have only zeros and ones. Okay, so suppose I have one pattern which is 0 0 0 1 1 and another pattern which is 1 0 1 0 0, and I want to find the distance between these 2 points. So, that is what is called the Hamming distance. Okay, whenever the 2 points differ, okay, for example, here here it is 0 and here it is 1. Okay, so we can say if you see in how many of them it's different. So, in 4 out of the 5 it is different. So, the Hamming distance between these two is 4. Okay. So, that is how you find the Hamming distance. Now, what happens is that suppose the values that you have are very much different. Okay. For example, I can have one pattern which has, say, the suppose the first feature. Okay, so, the feature 1 is 1 and feature 2 is 3 and feature 3 is something like, say, 1000 or something, right. So, if you are going to use these values as it is, you find that more importance will be given to feature 3 than to feature 1 and 2. So, because of this, what is used is you use some type of a normalization. So, you take all the feature 1 values in your data set, okay, and you can compute the you compute the mean of all those values and the standard deviation, and every value you say you take the value minus mu I divided by sigma I. So, if you do this, you will get values which are between 0 and 1, and you can then use those values instead of the original values. So, this type of thing is what is called the normalization of the values, and the idea is you give the same importance to all the features in your data set. And in the case of vectors, you talk about Mahalanobis distance, which takes into account the covariance. Okay, that is equivalent to something like what we have done here basically. Okay, so what are the variations of the nearest neighbor algorithm? You have what is called the KNN algorithm, that is a k nearest neighbors, and the MKNN algorithm. So, MKNN, and you have the RNN algorithm. Okay, so, let us see what are these variations. So, if you take the KNN algorithm, you need to of course give a value for k. Okay. So, the k is the number of neighbors that you are going to consider. So, generally something like k is equal to 5 can be used. So, that is the general thing that is used. So, what you do is if you have a pattern P, you find the k nearest neighbors of P and take the majority class of these points. So, suppose I have 5 points and suppose there are 3 classes and the first neighbor has class 1, the second neighbor has class 2, the third neighbor again has class 1, okay, the fourth neighbor has class 2 and the fifth neighbor has again class 1. Then the majority will be class 1. So, you put it as belonging to class 1 and obviously the value of k is crucial. And how do you determine it experimentally? You take the training data, divide it into 2 parts and use the first part as the training data and second part as the validation data. So, in the validation, so you use different values of k and you classify V using T, and the one which gives the highest classification. So, the minimum error in classification, you use that k. Okay, so, that is how you can do this by experimentation. The next is what is called the modified KNN algorithms. So, again you take k neighbors and they are weighted according to their distance from P. Okay. So, the closest pattern will have the largest weight. So, the closest pattern, okay, if dk is equal to d1, which means that is the closest pattern, then your wj, the weight given to that is 1. Otherwise, if your dk not equal to d1, you find this weight, and this weight will decrease as you go further away from the pattern. So, each pattern depending on its distance from your pattern P, you will have the weights. So, once you have these weights, you also know to which class these weights, these particular patterns belong. So, then once you do that, you take for each class, for example, you take class 1 say, and all the weights which belong to class 1, you add those up. Then you take class 2 and take all the weights that belong to class 2, etc., and see which class has the largest weight, and then assign the pattern to that class. The third one is called the R near neighbors. So, what you do in the R near neighbors is that instead of taking say k neighbors or some number of neighbors, you draw a ball of radius r. So, you decide some radius r and you draw a ball of radius r and you get BR. So, if you take BR, you take all the points which fall inside this, okay, in this ball, and you find the majority of those of the classes of those points. So, the what happens here is that in case the neighbors are too far away, okay, so taking k nearest neighbors does not make sense. So, in one way this taking a radius helps because it eliminates all the outliers that you have, and suppose your BR is empty, it assigns the pattern to the majority class. So, that is how it takes care of ties or where it is not able to assign, right. So, this is what is called the nearest neighbor algorithm. Next we come to the rule based classifiers. So, in the rule based classifiers you have the if then rules. So, if this features this, this features this, etc., then it belongs to this class. So, the if part of it is called the rule antecedent or precondition, and the then part is called the rule consequent. So, the antecedent will consist of condition of one or more attributes or features. Okay, so if this feature has this value, if this feature has this value, etc. And if you have more than one, of course, they are all ANDed together, and the consequent part is the class label. So, rule induction, if you have a data set, you can use rule induction by using these type of algorithm, which is called the sequential covering algorithm, and you have some commercial packages like Ripper, CN2, Holtz, 1R, etc. Okay. One more way of getting the rules is that you form the decision tree. Okay, so once you form the decision tree, from the decision tree you can get the rules. So suppose I have a decision tree, and suppose this is your the final leaf nodes in the decision tree gives you the class label, right. So if we go from the root node to the leaf node, it will tell you, it will give you a rule. Okay, so for example, if this is according to feature 1, this is feature 2, this is feature 3, etc., then you would get a rule which says if feature 1 equals something and feature 2 equals whatever plus etc., then the class label is 1. So, you can get these type of rules from the decision tree. So, you first induce your decision tree, and taking the decision tree you can then get the rules. Okay, what are the characteristics of the rules? Because the rules are the important aspects of the rule based systems. So, you need when you have mutually exclusive rules, what does it mean? It means that every record is covered by only one rule. Okay. And what are exhaustive rules? It means that every possible combination of attribute values are covered by some rule or the other. Okay. So, that is what you call exhaustive rules. That is, each record is covered by at least one rule. So, the classifier has exhaustive coverage if it accounts for every possible combination of attribute values. So, now the rules that you have in a rule based system, they are ordered in a particular way. Okay. So, they are called ordered rules. So, when they are ordered, the idea is that you start from the top of the rules and then you see the rule which gets fired, okay, by different instances. So, the rules which appear first, okay, are ranked higher than the rules which appear later. Okay. So, if it gets fired by one rule at the beginning, then you do not go down further. Okay. Next type of ordering is class based ordering. Okay. Rules are ranked according to rule quality, or they are ranked according to the class. In other words, you put all the rules belonging to one class together. Okay. Then you go to the other class and put the rules belonging to that class, etc. So, what how do you evaluate the rules that you have, the rules that you are using? Okay. So, first of all, what is the accuracy of the rules? In other words, number of instances covered by the rule. Okay. So, suppose you have a particular rule, it will not cover all the instances, it may cover some of the instances, it may cover just one of the instances, etc. So, out of n totally n patterns, how many patterns does it cover? So, that gives you an idea of the accuracy of the rule. Next is what is called the Laplace score, where you take number of instance that is covered plus 1 divided by n plus k, where k is the number of classes, and you have the m estimate, which is equivalent to the Laplace score except for this probability which is given here. And now if this probability is sort of the same for all the classes, you are going to get 1 by k, which means this will go down to the same as the Laplace score. So, these are all evaluation scores for the rules that you are going to use in a rule based system basically. Okay, so, if you have a rule based system, what are the advantages that you can have? It is expressive, because if you have a new pattern which comes and you see which rule it fires, then you know why it belongs to, why it is being classified as belonging to a particular class. So, it is highly expressive, explanation ability is very high. It is easy to interpret, easy to generate, because once you have got the rules, you just have to go down the rule set, and it can classify new instances rapidly, and the performance is comparable to the decision tree. Okay. So, the decision tree and this are somewhat equivalent to each other. Okay, the next we will see the support vector machine. Okay, so, the support vector machine basically works on two classes. So, if you have patterns belonging to two classes, it tries to find the dividing hyperplane between them. Okay. For example, if we have say a class like this and you have another class of examples like this, it tries to find the dividing hyperplane between these two, and then when a new pattern comes, if this pattern will come to the left side of this dividing hyperplane, it will put it as belonging to one class, and if it comes to the right side, it will put it as belonging to this class. So, what you need to do in the SVM is actually find the equation of this line one or the plane, okay, because here we are talking about 2 dimensions, but it could have any number of dimensions, right. It will have say d dimensions if you have a d features, right. It will be a d dimensional plane. So, we call it a hyperplane. So, we try to find the equation of this hyperplane basically. So, what are the properties of the SVM? The SVM will construct a maximum margin separator. In other words, it tries to find a hyperplane which is as far away from the patterns which are at the boundary, right. So, that it generalizes well basically, that is the idea. Second one is that even if the patterns are not separable. So, what happens is, what do you mean by separable? So, if we have a class like this and we have a class like this where they are separated from each other, there is a lot of separation between these patterns and these patterns, then you call it a separable classes. They are actually separable, and if they are separable, it makes it easier to find the dividing hyperplane. Whereas, suppose I have patterns like this and I have the patterns which are sort of mixed up partly with that, then we can say they are not really separable. Okay. So, the two classes are not separable. So, if they are not separable, what they do is they use the what is known as the kernel trick. So, when you do that, in other words, you are transforming the patterns to a higher dimensional plane where they can be easily separated from each other. So, that is what is being done. And SVMs are non-parametric method. They use the complete training examples, but the thing here is that it is the patterns which are at the boundary which makes a difference, right. So, the patterns which are far away from the boundary do not affect the hyperplane that you are actually finding. It is only the patterns which are there at the boundary. So, what happens is you do not need to use all the training examples, but you are only using the training examples which are there at the boundary. And but in spite of it, it is a non-parametric method. So, because of that, it is actually using the advantages of both parametric and non-parametric methods. Okay. So, both of them it is using the advantages of both the non-parametric and parametric models. So, now if we look at this figure here, we can see that the patterns, we have patterns of one class here, patterns of another class here, and we have this hyperplanes. Okay. So, these hyperplanes, they are all actually dividing the patterns into two classes. Okay. On the right side you have one class, on the left side you have the other class. So, which one do you use? So, we can say that we have almost infinite number of hyperplanes which we can get over here between the two. So, which is the hyperplane that we are going to use over here? So, now if we use this line on the left here, the leftmost extreme left one here, you find that it is very close to these patterns here. Okay. So, the idea is that if you have a pattern which belongs to this class which just sort of which is just on the other side of the boundary, then it is going to be misclassified. So, what you are trying to do basically is to find some hyperplane here which is far away from both these classes. Okay. That is what you mean by the maximum margin. Okay. So, that is what you are trying to do here. So, that is what is done here basically. Okay. So, what you do is you are finding the extreme point on this side, and if you draw one hyperplane there and the furthest point edge point of this class, and if you draw a hyperplane there, it tries to find a hyperplane which is in the middle of these two, right. So, it is trying to find the maximum distance here between this point and this point. So, that is what you do in the SVM basically. Okay. Another thing that you do is you are going to consider that one of these classes has a class label of 1 and the other one has a class label of -1. So, usually we use 0 and 1 if there are two classes, but here you will be using +1 and -1 basically. Okay. So, instead of minimizing expected empirical loss on the training data, SVMs attempt to minimize generalization loss. So, how does it do that? It finds the maximum margin separator. Okay. Now, if we look at the equation of the hyperplane which you are trying to find, it is going to be of this form. Okay. So, you are going to get w times x plus b is equal to 0, right. So, so b is of course the intercept that you have, right, and then w x, where w gives you the weight that you have for the various dimensions that you are going to use. So, what you need to do in the SVM is actually find the values of w and the value of b. Okay. So, these are the unknowns that we have. So, what is done is that you are going to model it like an optimization problem, and you are going to solve that optimization problem to get the values that we are actually looking for. Okay. So, this is how you are going to get the optimization problem. So, you've got a constrained optimization problem where you are trying to minimize this omega squared by 2, okay, subject to yi into w xi plus b is greater than or equal to 1 for I is equal to 1 to n, right, where this yi is either plus 1 or minus 1. So, yi we know is the class label, right. So, this value will be either plus 1 or minus 1, and you can use the convex optimization, the Lagrange multiplier method, that is what is used for solving this problem. Now, what happens if it is not separable? Okay, so, when it is not separable, so you can use this formulation, okay, where this eta is known as your slack variable. So, you are going to get minimize omega squared by 2 plus c times eta, okay, eta of I, and then the constraints will be of this form. So, what happens is that the formulation of the problem becomes a little more complicated, but these also can be solved by using the Lagrange method. So, what is what people basically do is that you have SVM formulations which are available online, and all you need to do is you give your training data into it, and it will give you your dividing hyperplane, and you will be able to classify the patterns using that, right. So, most people just make use of the commercial packages that are available online for doing this work. Okay. The next classifier we talk about is the Bayes classifier. So, in the Bayes classifier, you are trying to find the probability that it is a certain hypothesis given x, okay, given the pattern x. So, you get a new pattern x. So, you are using the Bayes theorem, which says that probability that it belongs to a certain hypothesis given h is equal to probability x given hypothesis I and probability h I divided by probability x, right. So, you are going to make use of this. So, when you have for a new pattern y, we need to find the posterior probability that it belongs to a particular class given y for a class C. Okay. Now, if we find this value, and the probability of error will be of course 1 minus that, and we classify y as belonging to the class C. So, you find this for every class that you have, and classify y as belonging to the class which gives maximum probability of C given y basically. Okay. So, that is how this actually works over here. So, let us look at the naive Bayes classifier. So, in the naive Bayes classifier, you are going to assume that all the features are independent of each other basically. Okay. So, we are trying to find probability that it belongs to a particular class given the values of the features f1 to fn. Okay. So, using Bayes rule, you are going to get probability of C given this is equal to probability of f1 f2 given C into Pc over P f1 f2, right. Now, since this is a normalizing factor, you can say this is proportional to Pc into because they are independent of each other, you are taking P of f1 given C into P of f2 given C, etc. So, if you can plug in all these values, then you can find the probability that it belongs to a certain class given these features, right. So, this is how your naive Bayes classifier works, and of course, this is an assumption that is made, but in many cases it is found to be working very well basically. Okay, so the decision tree classifier is the next classifier and we will do that in the next session. So, at this point we will stop this session and continue in the next session.